This problem and all other CALC 152 problems can be found here at Sarai Studies. Link is in the description box below. When I look at this, because I see two terms, I think telescoping. Because if you notice, telescoping always has two terms. This has two terms, two terms, two terms. But every test we've ever used, it's literally just one function. Same thing for LCT, ratio, and root. They're all just one thing. And the only thing I've seen that's two things, two terms, is telescoping. So that tells me, hey, try telescoping. The idea of telescoping is you take the limit as the numbers in the sequence of partial sums go to infinity. Sequence of partial sums is just a list of your sums. So you're adding the terms of your sequence up until 1, then up until 2, then up until 3, up until 4, and so on up until the last one. And if we want to take the limit of S sub n, well, we're not going to take the limit of just this. We have to have some sort of formula, some sort of function that we can take the limit of. So the idea of telescoping is that these sums end up just canceling out somehow. There's always a pattern, and you'll be left with a few or maybe just a couple terms that make up your S sub n, and then you can take the limit of that. How do you find out? Well, you just start by calculating the sums until you see a pattern. I always do up until 4, and you'll see why. The sum up until 1 is literally the sum when you plug in 1. And I started with S sub 1 because I saw this one here. If it was 0, then I would have started with S sub 0, meaning I would plug in 0 first. But we start with 1. This here becomes 2, so we have 5 to the first power, which is just 5, and then minus 5 to the 1/2. And we're going to keep things organized by adding parentheses, and then we're going to do the sum up until 2, because right now what you're looking for is a pattern, and I don't see no pattern here. So I'm going to do another one. So sum up until 2 includes a sum up until 2, so you have to include the sum of 1. So we bring that down here, and then we do plus the sum up until 2. So when you plug in 2, you get 5 to the 1/2 minus 2 here, that becomes a 3. So we have 5 to the 1/3. And then here I noticed something really interesting. This last term cancels out with this first term. But that's not enough to say it's a pattern because I only see it happening once. So I try again. Now I'm going to do S sub 3, which is a sum up until 3. So I have to include these sums. But you can always just add the last one because the sum up until 2 includes everything before it. So when you do plus and then plug in 3, so here would be 5 to the 1/3 minus 3 here becomes a 4, 5 to the 1/4. So again, the last term cancels out with the first term, and then I see this last term canceling out with this first term, right? Because this is a negative 5 to the 1/3, this is a positive 5 to the 1/3, so they cancel out. And so I'm seeing some sort of pattern, but to be sure, I always do up until S sub 4, so that includes a sum up until S sub 4, so all of these sums, and you can always just, again, add your last one, because that includes everything up until your last one. Then you do plus, and then when you plug in 4, you get 5 to the 1/4 minus 4 plus 1, that's 5, 5 to the 1/5. So again, last term cancels out with this first term, last term cancels out with this first term, and then this last term cancels out with this first term. So we realize that the pattern is that a last term cancels out a first term. And what we've been doing is we've been saying, okay, if we continue on adding, so as sub 5, as sub 6, and so on, all of this, then the pattern tells me that a last term will cancel out with some first term that's coming out later. So the only thing that's left is this 5 in the beginning. And then you would calculate your S sub n and then your S sub n minus 1, which we did in the video above this one over here. We did all of the work. We did the first half and then the last half, where we calculated S sub n minus 1, and then we found out what was missing. But here's a trick that's going to save you time. These problems where your last term cancels out first term, but it's canceling out right after it, like they're literally next to each other. This one cancels out this one, they're next to each other. This one cancels out this one, they're next to each other. Then you don't need to calculate the rest of it. So the trick is just go through every sum that you have and find out what's still there. Here it's the first term and the last term. First term and the last term. First term and the last term, first term and the last term. So this trick only works when your last term cancels out something right next to it. Then you can do this and realize, okay, what's left of every time I take a sum is the first term, which is 5, that never changes. But then these last terms are always left, but they're different. What am I going to do, right? 5 to the 1/2 and 5 to the 1/3 and all of that? No. You just ask yourself, what's another way to represent my last term? Well, literally with what gives you the last term, which is this over here. So you would just do minus 5 to the 1 over n plus 1, and that is your sequence of partial sums. So that's the trick. Then you want to take the limit of your sequence of partial sums as the numbers in the sequence go to infinity, and it's 5 minus 5 to the 1 over n plus 1. This becomes 5 minus 5. When you plug in infinity, you get infinity plus 1. What's a plus 1 going to do? Nothing, so it's just infinity. 1 whole divided into infinitely many pieces becomes infinitely smaller, so small, it goes to 0. and anything to the 0 is just 1. Then we have 5 minus 1, which is 4, and that's our answer. Because the limit exists, we can say that this series converges to 4. And that's it for this video. I'll see you in the next.